So in this section, we are going to look at the relationship between the factors of a polynomial and its zeros. And to make things easier, we're going to look at an example. Okay, to look at the elements of theory I want to introduce here. So consider a polynomial function f. And f of x is so here is consider any polynomial function, but just to make things a little more explicit, let's look at one in particular, this one. Okay, say we divide f by x plus 1. Okay, what do we get? Well, let's do the division algorithm. Okay, x times what will give me 3x squared? X times 3x. That gives me 3x squared plus 3x. Subtract. I get 8x plus 6. X times what is 8x? X times 8. 8 times x plus 1 is 8x plus 8. I subtract, I get minus 2, and I stop because the degree here, which is 0, is less than the degree of the divisor, which was 1. So I cannot fit, in other words, x into minus 2, so I just stop there. So it tells me that x plus 1 is not a factor of the polynomial because it didn't give me a remainder of 0. Okay, so that's one thing. Okay, so what I get from this is that f of x is the divisor times the quotient, 3x plus 8, plus the remainder, like that. Okay. Now there's value that we can easily find that makes x plus 1 0. And it's minus 1. So let's see what happens if we replace x by minus 1 in this expression. Okay. F of minus 1 is going to give us minus 1 plus 1. So clearly 0 here times some other stuff that we don't care about, because eventually multiplying by 0 will just give me 0 minus 2. Okay. So what I get here is, this is 0 times, I can calculate the other number. It's minus 3 plus 8, so it's 5. But it doesn't matter, like, it's going to be 0 times that. So it's going to be essentially minus 2. Okay? So if you choose for x the value that makes the divisor equal to 0, which is in this case minus 1, you're going to get the remainder. So this is something we're going to write down because it's kind of important. Okay? So if we calculate f of k, okay, it's going to be the remainder of f of x that we divide by x minus k. Okay, if you're not too sure what I wrote there, I wrote this general statement. We looked at a particular case. F of minus 1 is the remainder of our function f of x divided by x minus minus 1. In other words, x plus 1. But that's true for, it's not just, I chose x plus 1, with that I could have chosen any divisor of the form x minus k, and I would have attained the same conclusion. F of k would have been the remainder of that division. Okay, so we're going to frame that. Another way to see this, if you're not convinced, is that if you take your polynomial f of x and you divide it by x minus k, it's going to be equal to some quotient, q of x times x minus k plus a remainder. Okay? And if we just replace x by k, look what happens. It's going to be q of k times 0, because k minus k is 0, plus r. Now the remainder, like I wrote r of x, but it's actually going to, I could just write r because it's going to be a constant, since it has a degree lower than x minus x, and the only way for that to happen is that if it's a constant. Okay, so so in other words, our this expression here is just equal to r. So f of k is r, so which is the remainder. Okay. Let's keep going. This is important, but it's not actually the important, the most important statement of this section. Let's look at the case where k is not any number; it's actually a zero of our polynomial. Say k is a zero of f of x. Then in that case, f of k will be 0. Okay. That's going to imply that 0 is the remainder. So this is where I'm applying the frame statement above. So if f of k is 0, it means 0 is the remainder of f of x, which I divide by x minus k. Okay? So that's going to mean that f of x is going to be equal to some quotient times x minus k plus a remainder of 0. So in other words, f of x is q of x times x minus k. Q of x being this is a polynomial, right? So what we get from this is that x minus k is a factor of f. This is the important thing to realize. So if you've got a 0, like if k is a 0, automatically you have access to a factor of the polynomial of f. So we're going to frame that because that's pretty important. So if k is a 0 of a polynomial f of x, then x minus k automatically is a factor. So if we have access to the 0 of a polynomial, we have access to one of its factors, and vice versa, by the way, because if x minus k is a factor, automatically we know that from that factor we can recover a 0. We can recover that x equals k is a 0. So it's actually it's an if and only if. So we'll show that principle in action. Okay. So example. So for example, consider the polynomial 3x squared plus 11x plus 6. Okay. Let's replace x by minus 3 just to see what happens. We get 3 times minus 3 squared plus 11 times minus 3 plus 6. And that's going to be 27 minus 33 plus 6. And that gives us 0. Okay. So from this we get minus 3 is a 0 of f. Okay. Okay. And that's equivalent to saying that x minus minus 3, okay, which is x plus 3, is a factor of f. Okay. So let's check this, that this actually is correct just by factoring it. So by factoring, we should find x plus 3 eventually as one of its factors. So here I've got a quadratic polynomial, so I can apply the AC method. So I need to find two numbers such that their product is 18, sum is 11, so that's 2 and 9. So I'll write 9x plus 2x plus 6. I factor by grouping. And you can see this x plus 3 showing up, okay? Which is indeed a factor of my polynomial. Okay, so it works.